My name is Chuck Piercey. I'm a product manager at TidalScale. I'm actually one of the 4 co-founders. Want to say thanks to Stanford for hosting this event. It's a wonderful campus and university. Thanks to the UseR conference for having us speak. And then thanks to my own dev team. They're a fantastic world-class group of individuals. I'm going to break this down into 3 parts today. I'm going to give a little background on TidalScale, and then talk about the R benchmark we run, and then go through the results. And basically, the takeaway from today's talk is to show how and demonstrate how, with open source R, you can simply scale up on very large data sets without any extra API work or tools or sharding or anything using a distributed hypervisor. And we'll demonstrate that with R. So the problem, of course, as you know, is that there's huge amounts of data that we have to deal with. And it isn't just volume, it's actually the number of sources, the granularity, the level of detail. It's just becoming a tidal wave. And one of the speaker from Oracle earlier today said it best. He said, you know, any data you're looking at is actually just the tip of the iceberg. So that's just a fact. The next fact is, of course, we want to do any analysis we do in RAM, because that's just where you're going to get the best performance, the best interactivity. It exposes for you the power of the interactivity of R. And that's challenging because, as you know, the minute you start doing algorithms, it expands in memory O to the n squared, right, where n is the number of observations. And then the last statement to kind of put out there is that today you're faced with really 2 options that seem to be mutually exclusive. One is you spend a lot of money and get a very expensive scale-up system. And the other is you use standard hardware, but then you have to learn a bunch of tools and code to different APIs to do scale out and shard and partition your data. So I'm going to talk about another option that TidalScale offers that I think is of interest for these large kind of data problems. But to do so, I'm going to talk about virtualization first. How many people here have used VMware or Zen or... Good, okay, so you're all experts in virtualization. Virtualization is interesting. Virtualization basically lies to your guest OS. You know, each virtual machine runs on a piece of software called a hypervisor, and the hypervisor actually manages access to the hardware underneath. You can't see that there, but there's actually hardware. And you use virtual machine tools to migrate between different physical systems. So it does this by dividing the world into virtual resources and physical resources. The virtual resources, the system in the guest OS actually doesn't know they're not physical. It just sees a CPU, a disk, RAM, network. And then the hypervisor is actually sharing multiple VMs to the physical resource. And the whole magic of this is that the guest never knows. You boot Windows on your Mac, the Windows machine thinks it's looking at a 1 GB system, when in fact your Mac might be 16 gig, or vice versa. So that's what virtualization does. So the question is, you know, what would all this have to do with big data and TidalScale? Well, TidalScale, we've written a hypervisor, but it's a distributed hypervisor. It's a little piece of software that runs on each of the physical servers, and just like ordinary virtualization, the guest OS doesn't know. We lie completely, right? We tell the guest OS, you got a 10 terabyte system and 400 cores. But in fact, there are a bunch of different discrete servers, and we add up the physical hardware into a single virtual machine. Sounds crazy, right? But it actually works. And the reason it works for us is we have mobilized all those virtual resources. So instead of having VMs stuck to a server, not VMs, the resource stuck to a server, we can flow the CPU, that virtual CPU, we can flow it around the system. So the data can be co-located with the memory it needs can be co-located with the CPU. At any time, the distance between CPU and RAM, we try to make it 1. So we have a cost function that's constantly making the system resources flow together for optimal performance. So that's TidalScale. The net is TidalScale lets you build big machines for less, because you can use standard servers and just add them up. Take 10 128 gig machines, boot them as a single TidalScale system. Now you have a 1.28 terabyte system, but you've used standard hardware to do it. Now, I interviewed a bunch of people during the first 2 years of our company, almost 1,000 customer interviews. And there's use cases for this, both for convenience and actually just making stuff possible all over your IT stack. Simulation, of course, where the different pieces of the puzzle need to actually see each other to work, huge use case. Bioinformatics, which is a special case of simulation in many cases. In-memory databases. So just turning on the configuration in a standard MySQL database so that it puts everything in RAM, just cache stuff in RAM, make the cache 85% of your 10 terabyte system, you'll find that a lot of databases actually fit completely in RAM. And then the last, of course, is data mining, machine learning. And that led me through all the customer interviews to R. So R is a fantastic program for large data analytics, but it really wants memory. In fact, R seems pathologically in need of memory. I can make it go over the memory cliff, and it just wants to go there. So the challenge we had was, here's this application that wants a lot of memory, and here's TidalScale that can give you a lot of memory, a lot of cores. So how do you demonstrate that? So I went in search of benchmarks that would show this value, and I couldn't find any benchmarks that actually went big enough for what we can do. So we had to write our own. How many people here have written benchmarks? Anyone? One guy. Is it easy? No, it's a pain in the ass, right? So a year later, I can tell you this was a pain in the ass to do. But we wrote a benchmark, and we used the health insurance claim data set from the Medicare services site. They can go up to 680 gig, that data set. It's literally, I'll go through it in a second, but it's trying to solve the problem of how you process insurance claims. That was the customer use case that we're representing here. You have 70 gig of raw data input, but when you use the algorithms that we wrote to, it expands to almost 680 gig. And then we're going to run it on a single bare metal 128 gig server and compare that to a 5-node TidalScale system using the same 128 gig nodes, right? So apples to apples, literally the same hardware. We're comparing bare metal to TidalScale's virtualization. Here's the algorithm, and I won't go into details here, just suffice it to say I use 13 fairly standard R packages, and then we just time them. And we include the load time and the join time. So we count all the time. You could cherry pick this and actually just look at the in-memory analysis times, and this would look a lot better. A little bit more detail about the data set itself. If you takes one sample, so each data set has 20 samples. So here's the input files for one sample. And when you join them, when you load them, they're 6 gig. You join them, you get to almost 16 gig. And then as you apply the algorithms, it occupies more RAM in memory, up to 18 gig per sample. Now that's according to R. According to TOP, actually, that 18 gig is in fact 34 gig, or at least TOP says it's 34 gig. And you can see that's how we get up to the 680 gig. So when you load 20 samples, you're at 680 gig in RAM in R, and then a little detail on the data set. So what were the results? This is the bare metal results. The red line is showing you execution time, that's the y-axis, and then charted against, it's a scatter plot charted against our in-memory data size in gigabytes. And you can literally see the memory cliff here. It performs pretty well up to the sample size 5 samples in RAM, which is 90 gig according to R and 170 gig according to TOP, after which time it just plummets. It starts paging to and from disk. And in fact, the paging to, this is not disk actually, it's paging to and from SSD. And that first data point, 228,000 minutes, that's about a half a year, or 0.45 of a year. So the rest of that I had to calculate from SSD specs. So it's actually best case. So this is an example of why you want stuff to be in memory. Because the minute you go over the cliff, things become impractical to do. So what happened with TidalScale? Here's the TidalScale curve. And you can see at the low end, when we're comparing single server to single server, that the times are whatever that ratio is, 1.6, I guess. But then it flattens out once we start migrating across the nodes. And then you can see here, as we're going out, it follows pretty much linear. And that's running across, and I tried to place it correctly. That last data point is smeared thoroughly across 5 servers. So there's tons of migration going on there. So the summary there is that without any sharding, without any code changes, you get in-memory performance across 5 nodes, literally using the code that I developed on my Mac, and then scaling that up across 5 machines. And across all that curve, it was ranged from 240 to 550 times faster compared to SSD, fast SSD. You might ask, why does that work? And I'll go back to a little bit of theory here. How many people know the memory hierarchy? Are familiar with it? Great, okay. This is the memory hierarchy in actual latency, current, and I've updated this for NVMe flash. And then I tried to scale it as if one CPU cycle was 1 second. So on the right, I'm trying to turn that into human terms. What does that mean? So if one CPU cycle was 1 second, then level 1 cache RAM access is 3 seconds. An ordinary RAM access is 3 minutes. And then you jump to flash, where the access time is 1 week, right? What TidalScale has effectively done is, by being able to migrate resources, those 2 extra lines, memory over Ethernet and CPU context state transfer, that's where we're shipping the virtual resources across the nodes, has introduced kind of a level 4 cache, is the way to think about it. So we keep you closer to the RAM operating zone than to the SSD or any other storage media. So in summary, TidalScale gives you flexibility. Now you've turned the table upside down. You can size the system to the size of your problem, not force yourself into a bunch of tools where you size your problem into the bits that fit on systems. You can do it with standard server hardware, and you can expand as you need. It's fast. It gives you in-memory performance at large scale. That's 5, 10, 50 terabytes or more, and that's dozens to hundreds of CPU cores. In fact, we just booted with IBM software. We actually booted a 15 terabyte 400 core system in their San Jose data center just last week. And it's easy. There's no change to the OS, no change to applications. Everything just works. And we're optimizing for performance all the time. That's it for me. I got one more thing to say is if you have a big data problem, we're looking for workloads to test with. So you can come try it yourself on our POC systems down in Santa Clara. Thank you.